Thanks very much, everyone. So I'm here both representing Google, where I'm a product manager, as well as representing the Alliance for Open Media and our efforts to create a next-generation codec in AV1. And this is kind of a nice experience to be able to follow some other codec speakers who've already presented. So you're going to be seeing a little bit of some building on top of the presentation that Jonathan just gave, and also in terms of building onto the keynote from this morning. So hopefully you can refresh your minds, and I'll try to help you out with some of the things that Jen shared at the beginning, because I think he did a great job of kind of laying out the overall ecosystem in which we've been working. And some of the motivations for our work. And I wanted to start off by actually talking about that from Google's perspective. I certainly know when I started working on the project, it wasn't clear to me why Google would be working on codecs. It wasn't necessarily an intuitive place for them to be working, but I think we've all heard about some of the benefits in terms of savings in egress, potentially savings in storage, some potential upsides, and then a trade-off, how those costs compare to extra CPU expenses or licenses, depending on the codec involved. And I think the aspect that Jan raised at the beginning this morning that we didn't dig into as much is what the actual experience is like for users. And thankfully, AV1 is actually kind of Google's second or third time, depending on how you count, at looking at an open codec and sort of upgrading their codec ecosystem. And in the form of YouTube, we actually have some pretty great data about what it looks like when you switch codecs. So this is some older data from when we first did the jump from 264 to VP9. This was, in our view, a generational jump, very similar to the 264-265 distinction. We've sort of consistently seen the same results that Netflix has seen about VP9 and 265 being quite similar in performance. And this, to me, is sort of the key number, the one that kind of underlies all of the work that we're doing. And that's in terms of actual user behavior. We were able to do pretty clear A/B experiments with the essentially same content, in one case encoded with 264, in the other case encoded with VP9, to the same endpoint devices and just do a random experiment between codecs. And you're able to sort of see the difference in terms of watch time, particularly in regions where your internet connection is going to be weaker, where bandwidth is a tighter constraint. There's some great advantages. And so, you know, these numbers are a couple years old now, and so in the last 3 or 4 years, what this means is that just from YouTube alone, we consider VP9 a success, right? We've paid for the project in terms of not just the sort of egress savings that we've talked about from this morning, but also just in terms of increased ad revenue and sort of the benefits from an increased level of engagement from our users. And this comes from all the places you'd expect it, right? It's reducing the amount of times that users run into rebuffering events. It's shortening the time to first display on glass because of the sort of first packet size being, or the first segment being smaller. And so this is something that has really driven our investment in a next generation codec. And that's our work within the Alliance for Open Media and working on AV1. Again, this is something an area that we've been happy to work in for quite a while. And I think, as Jan rightly pointed out, the royalty situation for HEVC brought quite a few other companies into our way of thinking. And so we've gotten to be quite a large group right now. You'll see the latest edition at the bottom there just from a couple weeks ago, the announcement of Facebook joining the Alliance. The only negative of that is it kind of ruined our little slide here. Now we have 31 companies. It doesn't display quite as well, but we're happy to have them. It's totally worth it. And just outlining some of the goals here for the Alliance, right? We're trying to create a next-generation codec that's state-of-the-art for the web, and that's not restricted to just royalty-free. We really want to be the best codec possible. But at the same time, we do maintain sort of the open source and royalty-free philosophies that we had with VP9 and VP8. And again, speed of deployment is a key aspect for us, right? We want to actually get to market as fast as possible and actually have success with adoption, with endpoint deployments, with hardware adoption, really have a full ecosystem in place. And that's, I think, really the driving force behind the companies that we have. So just looking at the companies listed, we're able to get a sense of the types of use cases that we're targeting. Let's break that down a little bit. So on the sort of video on demand side of things, thinking about sort of streaming internet use cases, I think as a number of speakers have pointed out, there's sort of these two buckets to think of. The studio content, sort of high value content case. You can think of this as if you're trying to get a movie through sort of Amazon, through Google Play, if you're trying to watch Netflix, really any kind of media that's going to be content encrypted, media that's going to be have to be at the highest possible quality, and you're really going to be focused on maintaining quality, and you're potentially going to be willing to expend quite a lot of CPU effort on encoding cost in order to make sure that you really get your savings down, because this is going to be content that you're going to be serving many, many times over. On the other side of the spectrum is the user-generated case, the YouTubes, the Facebooks of the world, where you're really getting a tremendous amount of content, and making sure that you have something that can scale to actually encode all that content is essential, and you're willing to potentially have a less efficient encoding, very slightly less efficient, in order to make sure that your CPU costs are effective. And both of these use cases are going to be important for AV1. They're both factored into our development process. And on the live side, there's sort of an equivalent two cases. The sort of broadcast case, again, mirroring a lot of the talks we heard from this morning, of can you replicate or improve upon the TV experience over the web, and sort of maintain the same quality, the same SLAs, the same reduction in latency time. And then moving further down the latency side, potentially at the expense of quality, the real-time communication cases where you're really focused on having interaction, where you're trying to have two different encode points both transmitting to each other. Again, both of these are covered extensively by the companies listed. So with that in mind, what is it that we're actually trying to accomplish? Well, this is sort of an introductory list. This is not necessarily exhaustive of everything we're trying to develop, but I think this gives a sense of what a fully fleshed out codec ecosystem would look like. If we're able to obviously start with the specification, have a bitstream freeze, but then beyond that, really think about what it means to encapsulate this in many different sort of formats that we've talked about today, right? We've looked at bindings for MP4, for WebM and Matroska, as well as some of the newer options like making sure that we're working well with CMAF. We've talked about having the reference encoder and decoder available to the ecosystem. Starting point probably being the research work that we've already done and the encoder and decoder that we use for our research purposes. But beyond that, we're interested in creating production-capable encoders and decoders that are platform-specific and really drives everyone in the ecosystem to try to beat a very high usable bar for encode and decode. On the hardware side, we've had a history at Google of having a hardware team that provides a reference architecture for silicon manufacturers so that they can do their work as fast as possible. That's something that we plan to continue, and now we actually have a number of hardware companies working with us in that process, and so we've had even more progress in our hardware design compared to where we were with VP9 at the same stage a few years ago. And then making sure that we have a complete feedback loop on the ecosystem for testing, making sure that we're able to confirm our results, et cetera. So where we are today is quite a bit further than hopefully where we last presented a slide like this. You'll see at the top headline, sort of 63 tools have been through a technical integration process, and this is really, each tool is sort of an algorithmic submission, and we'll go into more detail about that from one of the member companies. There's a few companies, Google, Mozilla, Cisco primarily, who've had codec development teams in the past, and so those are obviously sort of leading the effort. And there's a few tools, the 5 tools listed, that are conditionally adopted. And the reason I mention them is really to highlight the fact that this has been an iterative process, right? So all the tools that we've had have been through reviews with the hardware subgroup, with the other technical groups, in order to ensure that what we're putting in is not just sort of one company's idea, but an idea that has been viewed by all the different member companies and all the technical teams we have. And so we do have those moments where we take a tool, have changes made, resubmit it, and do a second review. And then that last step of 26 tools under review, that's sort of the pool of tools available. There's not an expectation that we're going to add in 26 more tools. It's not to say that we're only 2/3 of the way done or whatever that number would be. Rather, that's sort of the pool of tools that we're going to try to pull in at the last second just to make sure that we are getting the most valuable gains. But there's certainly tools that we're willing to say, you know what, there might be something here, but it's going to take a long time to figure out, so let's just figure it out for a future codec. And many of those 26 tools will be part of that process. So what do they look like? Well, this is, again, sort of just an introduction slide. It doesn't go into an exhaustive list, but it gives you a sense of both the overall structure of the codec, which should be familiar for anyone who's done codec development work, right? At the very highest levels, we're not talking about anything shocking. You have sort of your entropy steps in order to be efficient with your tokens, the intra and inter predictions, and those do work together in many cases. There's improvements that we've made to the prediction block sizes under the partitioning area, as well as the transforms. And then quantization and filters, sort of where we're introducing error in the form of quantization and actually reducing sort of the amount of data being transmitted. And then the filtering side, which is essentially trying to replace that process as much as possible and see if we can extrapolate some information that has been lost and produce a better output result. Now, the detail underneath each of those categories represents the actual work that's been done on the codec. And both individual tools or individual algorithms and groups of algorithms that have kind of come together in an area. And the reality is, this is not a presentation I can give in 10 minutes, right? This is one slide that one of my engineers shared for just a prediction area. So just a subset of what I had on the previous slide. And, there's basically two types of people who work in this space. There's the folks who see something like this and say, yeah, I understand that. That helped me understand the codec. And I think the vast majority of us who look at that and think that is not a helpful way of representing information. So I'm not going to focus on this level of detail. And instead, what I'd like to do in the time available is just to focus on a couple of examples of some of the tools that we put in. Again, focusing at a very high level, not going to get into the math, trying to keep it simple at 3 o'clock. But at the same time, I think all of these examples give an insight into how our process has worked, which hopefully helps to give you a view of what the last couple of years have been like. So the first one I want to talk about is sort of our view of interpredictions. The idea of having a compound interprediction, being able to incorporate different motion vectors or different reference frames is an old one. That was something that was available in VP9. That's something that's available in most modern codecs. What has been interesting in this process is rather than sort of have a really straightforward blend, which I think is what we had in VP9, you could sort of do a 50-50 across a partition block of two different motion vectors. We try to do work to actually have individual pixels have different motion vectors and try to think about what's the most efficient way to do that without declaring a motion vector for every pixel on your 4K frame. And so that's represented by sort of the letter M here on the right side, which is sort of a masking area for your partition block. And we've started to experiment with sort of what are the most efficient shapes to think about how motion vectors might work together within the same block space, right? And so you can think of sort of the darkened area here as one motion vector representing one reference to somewhere else in the bit stream, and the white area representing a different motion vector. And you'll notice that the lines are kind of blurry, and that's intentional. There's some level of overlap where it's not exactly one motion vector or the other. And the benefit that comes from this is not just that you're able to think about more complexity, great, that's everyone's favorite part of a codec, but what you're able to do is imagine how to sort of reduce the effect of having blocks be an element of your codec at all, right? Like we're all familiar with creating blocking artifacts as a result of your encode, and then having a sort of filtering process or post-processing to try to remove that with deblocking filters. This is actually trying to take away the concept of blocks when it comes to motion vectors, right? So if an object is passing through part of your block, you can have just that object area represented in one motion vector and the rest of the region not have that motion effect. And there's a lot more detail here. We have sort of global and local motion vector concepts of how we actually implement this in an efficient way. But at a high level, this is what we're accomplishing. And what that also lets us start to do is think about sort of old tools that have been lost is kind of how I think of this category, right? The idea of thinking, okay, what types of motion are there besides translational motion? How do you actually do skewing effects for objects? That's a very old concept. I mean, there's, sort of, I don't remember the exact MPEG codec, but it's, well more than 20 years old to have sort of those concepts in a codec. And the reality is it's always been computationally impossible to make this work in a practical way. The sort of matrices required in order to represent these types of shearing motions haven't been reasonable. And what we're able to do now is start to incorporate ways of representing this as different motion vectors, sort of as a gradient throughout the block, right? So if you imagine sort of just the horizontal or vertical shearing as different amounts of motion vector in a given direction applied throughout a rectangular or square block, that starts to give you the shearing effect by using the same algorithmic tools and the same matrices that we've used in the past. And so that maintains sort of the efficiency of our work, makes sure the decode is as straightforward as possible, makes it hardware compatible, but still allows us to start doing new transforms. New prediction and new motion vectors. So the second area is transforms. And this is sort of thinking about how we start to separate what the idea of blocks even are. And what I really wanted to highlight on this between sort of the purple and the green is that we've been sort of very tied in the past between what is a transform block and what is a prediction area. And those are starting to now deviate a little bit within AV1. We can have individual transforms for individual portions of a transform block. It gets very recursive and very confusing, but I promise you it does still maintain its efficiency. And we also added a number of transforms and a number of combinations of transforms. And so what I think I really wanted to capture with this is the fact that there's a lot in this codec that when you first look at it just feels like, well, let's just, crank up a dial that we had in a previous codec, right? There were, 10 ways of doing something in VP9. Let's come up with 20 ways of doing it for AV1. And I think the important message here is that it's not just sort of blindly throwing things to make the codec more complex. All the tools that we've adopted and all the features that we've pulled in are ones that we're confident we can algorithmically be reasonable about how we actually implement. And even if we haven't done all the encoding efficiencies already, we have evaluated all the tools for their potential to be optimized within a reasonable time frame of a few months to a year at the absolute max. And so that sort of gives you a sense of why we're choosing to do some of the complexities that we're doing, increasing the number of transforms up to 16, 4 in the vertical direction, 4 in the horizontal direction. Not an arbitrary choice. It's something we feel like we can select through. The last one I want to talk about is just how we're working together as a group. Because this example of the constrained directional enhancement filter, and I'll be honest, this is not an area that Google worked on. This was a Mozilla and Cisco collaboration, so I can't go into as much detail about how we did this. But at the highest level, this was a sort of joint proposal they made of sort of trying to figure out the direction of some of the ringing artifacts that you get from sort of straight edges getting sort of blurred over. So if you look at that kind of blurry shape at the top and what you really want is sort of a crisp line, by sort of applying directional filters, you can sort of figure out what direction that line was intended to be, how it ended up getting blurred, and then reverse some of that work. And there's a lot of sophisticated work that went into this. There was a paper that the folks wrote together, and it's still very, very complicated. This remains one of the slowest things that we have in the encoder. And so we've actually started to think about, is there a different way to do this? And so from the Google side, we started to think about if we can combine a number of simple filters and try to get the same outcome. That was a goal that we started sort of as an idea that came from the prior work that we saw from Cisco and from Mozilla, but kind of approached a different direction to try to get there in a more efficient way. So we're actually still trying to sort this out. I have a feeling we're going to end up going for this more variable loop filter, and this is, you can see the two individual vectors there are not very successful at predicting, but the sum is greater than, or the whole is greater than the sum of the parts in this case, and we're actually able to get a better filter than we would have otherwise expected. And so there's a number of cases like that where the collaboration has kind of gone back and forth, and we're really just picking the best outcome. And so that's I think, been a really interesting change to our process. So that's all I'm going to go to into technical depth. Let's think about a little bit of where we actually have gotten to. So results. Here's where we are right now in terms of, or excuse me, here's where we were as of a couple months ago for AV1 development. You'll see the data on there is from the end of September. And this is comparing AV1 versus VP9. We do some, as I talked about, some comparisons against X265 as well, and have seen those results to be essentially the same. And so we've published the ones that are comparing against VP9. And what we're seeing is mostly about 25% savings, pretty consistent with, I think, the results from that Netflix published on VMAF. And you know, this is not an exhaustive list of all the metrics that we use. We kind of throw in every metric that people suggest within our AOM group, and then each kind of company kind of looks at the ones that are most interesting to them. And what we've actually seen, which is nice, is that they actually agree pretty well at this stage, and that if you optimize for a given metric, you're usually able to get the outcome you want with the codec. We're doing a little bit better on live, and what's not captured on here is for sort of the screen content use cases that Jonathan talked about. We're actually doing significantly better. I think that's a place where AV1's doing quite well. So for things like screen sharing and things like that, we're getting something like 70% savings over VP9. And so what we're seeing with this is basically we're at a point with the codec where it would be a successful outcome if we decide to publish today. You know, like these savings, I think, are sort of in line with what Netflix, what YouTube have said would be the thresholds they would need to hit in order to launch a new codec and start to re-encode their content. That said, I think we're still shooting for sort of the 35% target with those sort of 5 tools in conditional range and another sort of 25 tools floating around. And we're actually closer to that today. I think the latest I heard was sort of 29, but we couldn't finish running the encodes, of course. And so those are sort of the results that are still coming. In terms of timeline, what we're looking at for soft bitstream freeze, I know we talked about doing that at the end of October. We decided to push it for those 5 tools to sort of the end of this month. And so we're sort of at a stage where we're happy with the codec, but we're just like trying to make sure that we have the exact right tools that we want. The vast majority of that work is done, and you know, we accordingly moved the bitstream freeze to January 2018, but really in the same time frame at this point. I think we're far enough along that dates are not moving as much, which is nice. We are also planning to do some demos. So obviously the folks at Bitmovin and Mozilla have had some demos out in Nightly, where they've just been sort of using the very latest Git hash and putting together a version of the codec that works. We thought about doing something a little bit more in-depth for Chrome and YouTube. So we actually went through and picked a specific stable point that we liked in the codec, which is actually very similar to the results you saw from sort of mid-September, and are using that to actually get into the dev channel of Chrome by the end of this month. So that's something that, you know, hopefully you can just go into, flip a flag, and start playing AV1 videos through the YouTube pipeline. So that's sort of just our confirmation end-to-end that everything works. It lets partners kind of test things out. Not necessarily meant for, you know, mass public consumption, but it sort of shows our usage. And just have links to more information. The last thing I wanted to touch on was sort of the complexity question, because I know that came up in the earlier talks. And you know, the codec is definitely very slow at the slowest setting today. It's you know, very much on the order of 200 or so times slower than VP9 for encode. But what I want to really highlight is for VP9 and other codecs that we've developed, the sort of absolute slowest mode has never been the mode that we've traditionally used. You know, at YouTube, we've used speed setting 2 as opposed to speed setting 0, and that actually makes quite a bit of difference on speed. It ends up being, you know, probably about 50 times faster. And so I think there's a version of AV1 that we're targeting by the end of the year to have that would be about 20 times slower than VP9, still slower than we like, but getting much closer, with only about 1% compression loss compared to our absolute maximum sort of research potential. So we published the research results with the absolute slowest settings, but we are hoping to have something that's close to usable by the end of the year. And of course, even after we freeze the bitstream, that's when we do the majority of our optimization work to really get things working as fast as possible, sort of within the 5 to 10x range of VP9 encode. And on the decode side, we're shooting to be 50% slower than VP9. So, you know, less than double decode complexity. So those are the targets we have. If you are interested in the technical stuff, for like the 3 of you in the room who wanted more, that last link there is the technical presentations from ISIP, where our engineering team really went into depth. It's a lot more of that crazy slide. There's like 100 other slides that go with that. So you can sort of get your heart's content there. You can actually look at the code base and sort of play with it, build a version yourself. We just went ahead and ran the test to build our own version of Chrome that successfully decoded some AV1 content with a pre-bitstream version. So, you know, that was a nice little internal moment for us. You can do the same thing. And then Are We Compressed Yet is a site where I grabbed those graphs from. You can sort of check the different runs of tools, sort of do your own mix and match, and actually test the results yourself against another codec you like. We have a ton of codecs on there and a ton of choices. The folks at Mozilla built that. So all that is available to you. We'd love to see more people participate. So if you have questions about that, certainly ask me. Thanks a lot.
Before we open up for questions, I just have to apologize because I got my cables mixed up. When I introduced you, I gave the introduction for the next speaker because the secret sauce about you was the fact that you had the summer job or high school job that I wish I had when I was in high school, which was working for Blockbuster, getting free movies every month. I wish I had that one.
Yeah, it's funny. I actually also have been traveling through multiple countries,
so
they
both wasn't
work.
Totally wrong.
Yeah, exactly.
But let's open up for questions.
So looking at that impressive list of companies that are part of the AV1 project or the Open Media Alliance, there's one that is definitely missing, being Apple. Is there any discussion, work, or any thoughts on trying to get them on board? Or I know it's difficult, but
I was hoping you weren't going to mention a company. We could speculate if it was IKEA or someone else. No, you know, obviously Apple is not listed. I would not take that as a sign that we haven't been talking with them. We see them pretty regularly at a bunch of meetups, and I wouldn't rule anything out at this point. Probably the most important thing to share is that is a list of companies who have contributed to the development of AV1. So that means that they have agreed to take their intellectual property and have it be contributed and supported for the effort. There's a bunch of legal agreements that went into sort of their role in protecting the use of IP for the project. That doesn't actually preclude anyone from supporting it, right? So there's a list of hardware companies on there that I think is pretty exhaustive, for example, but pretty much every major silicon company in the world we've talked to, and they're interested in supporting the codec, even if they're not using our reference hardware, for example. We've assisted them in building their own. So the list of companies that I think will have AV1 support in some fashion is much longer than the list that we showed. And I think that applies to any companies that you feel are missing as well.
Any more questions? Oh, there's one.
Yeah, so I think the STU is from H.263 version 2 from 98 actually. But regarding, and that's 20 years old, so that patent is sort of too old to be valuable or sort of valid anymore. But a lot of other tools seems to be similar to what you have in HEVC. So how do you go about to be sure that you don't infringe of the HEVC patents, which seem to be a lot of them?
Sure. Yeah. No, it's obviously something that we think about a lot, and I don't want to go too far into how we do our IP review process, but at the highest level, I'll say there's a couple philosophies that we use. One is we've kept our development team pretty much HEVC free. So actually one of the reasons that all of our comparisons are against VP9 is because our core engineering team doesn't actually run very much with HEVC, right? We pretty much have them work exclusively outside that code base to prevent them from being tainted. Also, there's sort of just the levels of review that we use for the codec development work. So each company has its own sort of IP review process that they do before they submit a tool. Internally within the group, they'll submit their view on any of the IP associated with the tool. And then we actually have sort of a joint pool of legal resources across the companies that we've set up. That was its own very complicated process to get all the companies to agree to something like that. But we're actually at a point where we're doing a separate sort of legal review board to ensure that IP is not being infringed on for the tool submissions. And so, yeah, I mean, there's absolutely the case that if we felt like a tool was an issue, we would remove it. So everything that's in there is basically tools that we feel like does not run into that problem.
Anyone else? No? Well, in that case, thank you very much, Jake.
Thanks.